I'm going to take a slight risk now because I have a time limit of approximately 55 minutes. So if I get ambushed by a hard problem, I will just have to stop in the middle, which will be unfortunate. But there we go. I'm continuing with problems from the book Problem Solving Strategies by Arthur Engel, and I'm working through the list of 60 problems from the first chapter called the Invariants principle. And I've got so far to number 44, so if I manage to do the next one, I'll be 3/4 of the way through, which will be exciting. So let's get going. Question 45, what does it ask? It says, accumulation of your computer rounding errors. I think that deserves to be written down. It's in boldface, which I can't compete with. What on earth can this be about? Start with x naught equals 1, y naught equals 0. And with your computer, obviously it's not actually literally asking me that, I suppose. With your computer, generate the sequences. Ooh, nasty formula coming up. xn plus 1 equals 5xn minus 12yn over 13. Those numbers 5, 12 and 13 ring a slight bell. Yn plus 1 equals 12xn plus 5yn over 13. So one thing I notice immediately is that the vector or do I? This looks suspicious as though it's going to have some kind of length preservation property, but I'll come to that in a minute. Oh, well, my suspicions are slightly confirmed by the next. But just because we're 5, 12, 13 triangle, if xn and yn were sort of orthogonal vectors, then this would, of unit vectors, then this would be another one. So find xn squared plus yn squared for n equals 10 squared, 10 cubed, 10 to the 4th, 10 to the 5th, 10 to the 6th, and 10 to the 7th. What on earth is all that about? So, I ought to be able to represent this as a matrix. In fact, I can, so let me just do that as a matrix multiplication. So xn plus 1, yn plus 1 equals a 13th, 5 minus 12, 12, 5, xn, yn. And so now we see that so this just looks like a rotation. So 5 squared plus 12 squared is 13. So the determinant of this is not in fact 1, but seems to be 13. Is that really the case, or am I being completely daft? No, I am being daft. Sorry, when I multiply by 1 over 13, I will multiply the determinant by 1 over 169. Sorry, the determinant is 1. So why isn't the answer just 1 all the way? Because I start off with So actually no, that doesn't follow unless this is a rotation. But is this a rotation? Well, the vectors 5, 12 and minus 12, 5 are pretty orthogonal, so this just is a rotation. Is there anything to this question, or is it just answer 1? I'm so sort of weirded out by that I'm actually going to work out what happens if I stick what x1 is. So x1 is 5/13 and y1 is 12/13. And so if I took x1 squared plus y1 squared, I'm going to get 1. Okay, I don't think there's much more point. Why does it say accumulation until computer rounding errors? I don't know. The next question. Unfortunately, this is a competition question, so at least it seems to be, because it's a competition I've not heard of. But so there's a serious risk that I'm going to fail to solve this in the time allotted. Start with 2 numbers, but let's have a go anyway. Don't be too defeatist about this. 18 and 19 on the blackboard. In one step, you may add another number equal to the sum of 2 preceding numbers. And it doesn't say the 2 preceding numbers, so just 2 preceding numbers. Can you reach the number 1994? That's quite nice. So it should be nice to think about, even if I don't manage to do it. And then it says I, M, and I don't know what I, M stands for. Now, this feels like an example of, so I've talked before about the tension between just messing about and seeing what you can do and actually thinking and trying to but I'm now confused a little bit by the question. Because it says equal to the sum of 2 preceding numbers. Does it mean the 2 preceding numbers or 2? It just says 2 preceding numbers. So if I'm allowed to just add any 2 numbers that I've had before, then all I seem to be asking is what is the closure, does the closure of the set 18, 19 under addition include the number 1994? And it seems to me rather obvious that it will, because up from 18 and 19 I can make so I suppose that slightly depends on whether I'm allowed to take 2 equal numbers. So from 18 and 19, can I make 36, 37 and 38? Probably not, actually, otherwise. So if I could, then from 18 and 19 I'd be able to make 36, 37 and 38. And then adding another 18 and 19 to these, I'd be able to make 54, up to 3 19s, so 57. And these intervals would expand and expand, and eventually I'd get to they'd start overlapping, and it's clear that 19 squared is under 400, so the overlapping is going to happen long before I get to 1994. So that can't be the question. So let's suppose I'm only allowed. So the next idea is I'm allowed to add. If it's another thing that I think can't be the question is if I just sort of start with 18 and 19 and then do a bit of a Fibonacci sequence. I just have to take the sum of those two, and I get 37, and then I add 19 to 37, and I get 56, and I add 37 to 56, and I get 93, and 56, and 93. I might as well just try this and see what happens, but I think this can't be the question. 149, 93 and 149 is 242. So it's growing exponentially, so I'll reach this not too long from now. So 371. No, 391, and then 242 and 391 is 633, and then I'll get, so I'm going to add it now, 4, 2, and 7, and 3, 1024, wow, some surprise. And then I'm going to miss 1994 by miles, so I get 16 something, and then after that. Yeah, so that would be a boring question, so it can't be that. So now let's just try I'm allowed to add any two preceding numbers, but they have to be different. So 37, and now I can add 37 to 18 and 19. So that'll give me, I'm going to work out the smallest things I can get at each stage. So 37 plus 18 is 55, and 37 plus 19 is 56. And now I will try 55 plus those three. So I took 19 plus its predecessors, then I took 37 plus its two predecessors, and I take 55 plus its three predecessors. So that's 55 and 18 is 73, then I have 74, and then 55 plus 37 is 92. And then I take 56 plus those things. So 56 plus 30, I get 74 and 75 now. I had 92, and then 56 plus 37 is 93. And I also have 56 plus 55, which is 111. And I suspect that this 92, 93 is going to go 93, 4, 94, 95 as well. Let's just check that. So 73 plus 18 actually gives me 91. I'll have 92, 93, 94. So that's from 91 up to 94. So it's giving me things that although I wasn't able to add 18 to 18, I could add something like 18, 19, and 37, because I can I can get 19 plus 37, I can get 18 plus that, and then I get 18 plus that. So it's looking very much as though you can reach the number 1994. Just because, again, these intervals are going to get wider and wider. But do they get wider and wider in time? Maybe that's not quite so obvious. Perhaps actually, no, that isn't so obvious, because well, actually, no, maybe it is. So I can add 18 or 19 to either of these, and I get these. And I can add 18 or 19 to any of these. That'll get me this. I can add 18 or 19 to any of these, and that'll get me another interval that's a bit wider. And so I think it's pretty much the same as it was when I was allowed to use 18. When I was allowed to add the same thing twice, it just takes a slightly longer. But the distance from 75 to 91 is only 16, so I'm not going to have to go very far before that these start to overlap. So I'm a bit confused by that. I can't work out an interpretation of the question that makes it an interesting question. I think I haven't understood the question, but I'm going to have to press on because I don't want to spend ages puzzling over that. This is another IIM question, so I'm still slightly worried. How long have I got? I've got half an hour or so, a bit longer, 40 minutes maybe. So I think that's a risk I can take. So in a regular A pentagon, B hexagon, all diagonals are drawn. Initially, each vertex and each point of intersection of the diagonals this again is going to need some interpretation, is labelled, I'll use English spelling today, by the number 1. In one step, it is permitted to change the signs of all numbers of a side or diagonal. Is it possible to change the signs of all labels to -1? By a sequence of steps. And it says IIM again. So my only anxiety, so that says a 1 there, let me just write that a bit more clearly, 1. My only anxiety about this is what a diagonal is. So I think in the case of a pentagon, it's fairly clear that a diagonal means one of these things. Which means that I have 1s at all these 5 points, 1s at all these 5 points. And so at each move I get to change the signs either on an edge or on a diagonal. The number of 1 signs starts off being 10, and I want to get from 10 right down to -10. It doesn't look as though there's a really obvious reason not to be able to do that, simply because these differ by a multiple of 4, and when I change from 4 lots of 1 to 4 lots of -1, I change the total by 8 then. But I can also change it by 4 by doing things on the side. So I'm going to try something fairly natural, which is wait a moment. If I were to change the signs on, maybe it's difficult actually to, if I just look at the inner pentagon, I'll see that it's difficult. What happens? So if I, for example, go around the inner pentagon once, then everything will end up having changed sign twice, which feels a little bit like the handshake lemma actually, but let's just think about. And similarly, if I go around everything, it actually feels, so a little remark that's occurring to me is that supposing I had a way of changing all the signs so again, the move I'm allowed to do is I'm allowed to take one of these lines, including one of the edge lines, and just change everything on that edge, on that line. So if it's 1 -1 -1 1, I could change it to -1 1 1 -1. Now, supposing I had a method that did that, then I could take that same method and I could just do it 5 times rotated. So I'd sort of first of all do it as I'd originally devised it, and I could rotate the entire pentagon, or equivalently rotate the method, so to speak, and just do it again. Then I could do it a 3rd time, and then I could do it a 4th time, and then I could do it a 5th time. By the time I'd done it a 5th time, I'd have changed sign 5 times, which would be the same as changing sign once. So that actually proves that if there's a way of doing it, then there's a way of doing it in which I use each line. It has a sort of symmetrical way of doing it. So if I use this line 3 times, I use this line 3 times, this line 3 times, this line 3 times, and this line 3 times. Now, if there's a symmetrical way of doing it, then there's no point in using a line more than once. Because if I do it twice, it just cancels out. So every time I use it twice, I might as well just not have done that. So that seems that there are only 2 candidates for how I might do it. Not 2, 4 candidates. Either I do nothing, so that's not a reasonable candidate, or I do this sort of inner 5 lines, or I do the outer 5 lines, or I do both the inner and the outer. But we see that if I do all the inner 5 lines, nothing happens, and if I do the outer 5 lines, nothing happens. So I reckon that the pentagon, it is not possible. So I didn't really do that by an invariant, but I'm quite pleased with the argument I came up with. So the argument I came up with is if there's a method of doing it, there is a rotationally symmetrical method of doing it, and there clearly isn't a rotationally symmetrical method of doing it. So I suppose buried inside there is a parity argument of sorts, but I don't feel particularly like uncovering it. Now the hexagon, I'm slightly doubtful about what the question means, but I'm going to assume that diagonal means chord, so it doesn't just mean something like that, but I'll put those in first though. Whoops, that's supposed to be just a single point. I'm going to assume that we get all these things in as well. I don't think this is going to be a very pretty picture. And now we've got a whole lot more points in the middle. So that's the question I'm going to think about anyway. Now here I can't use that symmetry argument because, well actually I can use a symmetry argument, but I can't do a symmetry argument by 6, because if I've got some method and I do it 6 times, that's going to cancel out that method. But what I can at least do by the same argument is argue that it's that the method is without loss of generality symmetric under rotation by 120 degrees, because that I have to do 3 times. So if I do whatever method I had, then I rotate it by 120 degrees and do it again, and then I rotate it by 120 degrees and do it again. It's the same as doing whatever method I had. So I can assume that if I've ever used this line, I'll use this line and this line. And then similarly, if I use this line, I'll use this line and this line. And if I use a diagonal going up a main diagonal, I'll use all 3 main diagonals. If I use an edge, I'll use the other 2 edges. So that's a way of saying, instead of saying I'm allowed to use any line at all, what I'm allowed to use is that. So in other words, I'm allowed to change everything on the boundary. That's just, I'm going to summarize it by saying I'm allowed to change everything on the boundary. I'm sort of imposing symmetry here. I'm allowed to change everything in one of those triangles. I'm allowed to change everything in that triangle rather, and everything in the opposite triangle. And the final thing I'm allowed to do is change everything in this star here. Now what happens if I change everything in that star here? And then each one of these, there's no point in doing more than once. It's a similar argument to what I had in the pentagon. So basically, I can say a little bit more. I can say I've got to change those 3 vertices, and now oh no, sorry, I can do the boundary. So point number, it actually puts a big constraint on. So if I don't use the boundary, then I've got to use 2 and 3. And if I use 2 and 3, then we've now changed the ones on the boundary. We've changed everything that goes round here once, and we haven't changed the middle. Have I changed it once? Let me just check that. No, I've changed. If I use 2 and 3, then actually that's not the case. So those points there are changed twice. In other words, they're back to where they started. So the ones in the middle here are changed 0 times. I mean, sorry, once each, and the ones on this boundary here are changed twice. It looks awfully as though I can't do it. So the only one of these that changes the middle is that. So I've got to use this. So that means that the boundary ones have now been changed. So if I now use the boundary again, I'm going to have to use this triangle and this triangle as well, because that'll be the only way of getting. So that's changed it to -1. The boundary would change it back to 1. So then I'd have to get to -1 again. So I'd have to use this to get those 3 to -1, and do this to get those 3 to -1. So one possibility is 1 plus 2 plus 3 plus 4. I'm using plus because I think of it as sort of addition mod 2, underlying what's going on here. what is the other possibility? The other possibility is that I do not use the boundary, but if I do not use the boundary, then I can't use, so then these are all -1, so I can't use this or this. And so that doesn't work. So the only possible thing is 1 plus 2 plus 3 plus 4. So we just have to ask ourselves, does that work? So it works for the center, it works for the boundary, but it doesn't seem to work for this point here because that is contained both in the right-facing triangle, right-pointing triangle, and in the left-pointing triangle. So my conclusion here is not possible again. And I think I'm going to stop because I don't, or if I have a peep at the next question and it looks hard, then I might not be able not to think about it. Perhaps I'll take that risk actually. Okay, I think it might be all right. So I'm risking one more. I haven't got that much longer to do it, but 48. In the figure, so there's a figure which I'm about to draw. So two squares are neighbours if they have a common boundary. Consider the following operation. T. Choose any two, perhaps this is going to be hard actually, neighbouring numbers. And add the same integer to them. Okay, that's quite nice. Can you transform figure 1.7 to figure 1.0? So can you get from this 1, 2, 3, 4, 5, 6, 7, 8, 9 to this? So this looks like a classic think of an invariant problem. So it's a good chance for me to try to be systematic. So 7, 8, 9, 6, 2, 4, 3, 5, 1. Okay, I like that. So I can add any integer, which obviously it must be necessarily that integer could be positive or negative, because otherwise there'd be no hope of, because otherwise the sum would go up all the time, which is obviously not going to happen. Is there anything nice about this pattern? Or is it some random, looks like some fairly random bunch of things. I have a little thought about even and odd permutations, except no, it's going to be problematic. Just because if I add, for example, 1 to 1 and 4, I've got 2 2s, and then I can't really think of that as a permutation. I can't put them in an order because the order is ambiguous and so on. So maybe parity of permutations is not going to help here. Could parity full stop help? Not very likely, because the sum of this is equal to the sum of this. But is there some other kind of parity consideration? Like, if I'm adding neighboring things, can I use some trick that looks at So if I'm adding neighbouring things and I want something to be preserved, then one thing that could be preserved is the sum of the ones on the black squares minus the sum of the ones on the white squares. That would be a... So what happened there? One sort of invariant that one can look for, as I've said many times, is you look at some kind of linear combination of the data that you have in front of you. So we would look at the numbers that's in that square, if that's A1, A2, and so on, and then our invariant would be sigma lambda I AI for some suitably chosen lambda i's. We want that to be invariant, so we want that if you add the same integer to this square and this square, say you've got sort of, that's lambda 1 associated with that square, lambda 2, then lambda 1 is going to have to be minus lambda 2. So the only reasonable invariant that I could choose is the sum of the ones on the black squares minus the sum of the ones on the white squares. So I'm assuming that they're going to be different. So let's just see what it is. We get 1, 6, 15, 18, 25, take away 20 is 5. 2, 4, 6, 8, average was 5. There were 4 of them, so that's why I got that the sum of this was 20. Please may this be different. So 7, 9, 10, 19, 22, take away 14 is 8, take away 9, I get minus 1. So it looks as though we not only can't get to this, we can't even remotely get to it. We can't. Have I made that calculation correctly? 16, 18, 21, 22, 17, 11, 7, minus 1. Just check this one. 1, minus 1, 2, minus 2, 3, minus 3, 4, minus 4, 5. Yes, okay, so that's done that question. Answer, no. And now, okay, so I think, okay, I'm going to do one more. This one looks as though it might be all right. There are several signs plus and minus on the blackboard. So it's a race against time, this question now. You may erase 2 signs and write instead plus if they are equal and minus if they are unequal. Then the last sign on the board. Okay, this is easy. Does not depend on the order of erasure. And there's an easy invariant there, which I can just see straight away, because it's obviously a parity question. If I think of these numbers as 1s and minus 1s instead of plus and minus, then it's just the product of all the numbers I've got. Because if I've got 2 things that are equal, and I replace them by a 1, or if I've got minus 1 and minus 1, I replace them by 1, then the product remains of... I've replaced something that had a product 1 by something that's got product 1, and if they're different and I replace them by a minus 1, then I've still preserved the product. And so at the end, whatever I've got is the product of what I had before. Okay, so I think I might have time yet for another one because it seems to be in a similar style. There are several letters I won't write it out just for this. So E's, A's and B's on a blackboard, lots of those. This will probably be a mod 3 thing or something. We may replace 2 E's by 1 E. So E is our 0, I would guess. 2 A's by 1. I think I'm solving this question before even seeing the question, really. 2 A's by 1 B. 2 B's by 1 A. And let me guess, an A and a B by 1 E. An A and an E by an A and a B and an E by a B. So A, E goes to A, B, E goes to B. Proves that the last letter does not depend on the order of erasure. So I just think of E as 0, A as 1 mod 2, B as 2 mod 2. If I've got 2, and I'm taking the sum mod 3. And you can just check that all of these preserve that invariant. So that was totally uninteresting, I'm afraid. Okay, so I've just seen another one, and it looked, I just got just from a sort of slight glimpse of it. I didn't fully see what the question was, so I'm not going to be cheating for next time. But it just had a little look about it that it might, it sort of could be quick, but might not. So I think since I've reached question 50, which is much more than I was expecting to do, although admittedly that's partly because one of them I'm not sure I even worked out what the right question was, and basically because they weren't super interesting questions today, except for actually this one about the symmetry idea. I was quite happy with that one. And actually I was quite happy with this one, not because it was very difficult, but because that felt to me like a clear example where I was able to do it more quickly than I would have been had I not gone through the previous 47 questions on this sheet. And 49 and 50 were not so amazing. So I hope that next time I'll have some slightly more challenging problems. But we'll see about that.